Swayam Prabha. Digital India. Educated India.
In this class, we shall discuss about the regenerative steam power cycle with closed type feed water heater. In the last class, we have discussed about the regenerative steam power cycle and we have seen the use of feed water heater and that was open type feed water heater. So, today if we try to just recall exactly what we have discussed in the last class. So, we have again I am drawing the schematic diagram of the so, this is the schematic depiction of the regenerative steam power cycle with open type feed water heater. What we have seen that making use of this device which is essentially a heat exchanger in which two streams, that is the extracted steam from the turbine is allowed to mix with the feed water which is coming from the condenser. So, the collected condensate would be pumped to this device wherein the extracted steam will be allowed to mix properly. Now, we have seen that as I have said just now that whether it is open type feed water heater or closed type feed water heater, these devices are basically heat exchangers. So, you know that in this, by making use of this, we could establish that the efficiency of the cycle can be increased, and we have discussed that if such a device can be increased or such a device can be can be integrated, I mean more than one such device can be integrated with this circuit, efficiency of the regenerative power cycle can be increased and efficiency would be closer to the Carnot cycle efficiency. But you know that practical limitations are there because of the initial cost as well as the cost which is involved with the operation of this device. So, accounting for these difficulties, the number of feed water heaters which is limited to 8, not more than that. So, today we shall discuss that instead of allowing two different streams. So, this is extracted stream and this is feed water. So, these two streams are mixing together in an open ambience. Open ambience means this is a closed device, but these two streams are directly mixing, there is no any interface. So, that is why the name open is coming. So, this is open space, two streams are coming and they are mixing directly with each other. Now, today we shall be discussing about the closed type feed water heater. And in this closed type feed water heater, the extracted steam will be allowed to pass over a circuit, over a coil, and feed water will be allowed to pass through the coil. So, this is essentially a cross flow type heat exchanger. So, let me draw it. Okay. So, I can draw the circuit here only. So, rather I can go to draw over here, this is boiler, this is turbine. Now, here we will be having one feed water heater and steam will be taken to this feed water heater, but so this is one pump, this pump is not required even, let me erase it. So, if I draw the so this is the coil through which this feed water will be pumped and this is condenser. You can see that this pump is responsible to develop pressure. So, the collected condensate will be pumped by this pump to the boiler pressure. Why? Because if we go back to the previous slide, here two streams are mixing together and definitely the steam which is extracted from the turbine is having different pressure than the pressure at which the feed water is supplied to this open feed water. Now, it is because of this reason the second pump was there, but in this case since the feed water will be allowed to pass through the coil, and if we can design properly, definitely we need to design properly, that is the frictional losses, and if we can select pump accordingly, then this pump will be able to cater feed water even up to the boiler pressure. So, there is no need of having additional pump as of now. So, this is the turbine idea is, so you can see this is a cross flow heat exchanger in which feed water is coming in this direction and which is needed to be heated by the steam which is extracted from the turbine. So, steam which is extracted from the turbine will be allowed to pass over this coil, and during the process, rather during this flow process, heat exchange will take place and feed water will gain heat from the extracted steam, and we can increase the temperature of feed water. So, you know that when steam is allowed to pass over the coil, it will lose heat and that heat will be gained by the feed water, and what will happen, the steam will be condensed. So, this condensed steam will be again there are two ways. If we need to supply that condensed steam to the feed water line, then definitely we need to have an additional pump, and that is why this additional pump will be required. So, this is P 2. So, these are different points. So, you can understand the collected condensate will be pumped back to the feed water line, and eventually we will be getting mixture at the inlet of the boiler. Okay. So, the feed water and the steam, so basically steam water mixture will be pumped to the boiler, and if I give the name, so this is 1, this is 2, then we can give name, this is 3, this is 4, this is, so 3 to 4, this is 3 4, say this is 4 and this is 4 prime, and we can give name that is 3 prime. So, this is 3 prime. So, this is 3 prime, this is 5, 6 and 7. So, we have identified several state points. Now, few minutes back we have discussed that the requirement of additional pump is not there in the circuit, but now we can see this pump is required, but requirement of this pump can be eliminated if we use steam trap. So, this is called steam trap. So, from the name itself you can understand this is again a device which will trap steam and will allow liquid to pass. So, the collected steam can be again cascaded back to the condenser using a throttle valve. So, that is what is. If we can use this steam trap, you can understand that the requirement of additional pump, which is really not advisable considering the cost associated with its operation as well as initial cost. So, the requirement of additional pump can be avoided if we use steam trap, and this device will only trap the steam and will allow liquid to pass. The steam which is collected can be cascaded back to the condenser using a throttle valve. So, this is the idea. So, this is what is the regenerative steam power cycle using a closed type feed water heater. Why it is closed type? You can understand two different streams are not mixing directly together, rather. So, this is steam flow and this is feed water. While feed water is passing through the coil, steam is allowed to pass over the coil, and during this process heat exchange, you know that feed water temperature can be increased before it enters into the boiler, and that is what is the objective of this particular cycle. So, somehow we are increasing the temperature of feed water, and that temperature rise is not coming from the combustion, that is that heat is not supplied into the boiler by burning fuel, but this amount of heating is done by extracting steam from the turbine. And we have seen that again I am repeating, you may ask me a question, because if we extract steam, that means we are not allowing that steam to do work. Had we allowed that steam to work in the turbine, we would have obtained more amount of work from the turbine, but we are not going to do that. Instead, we are extracting steam to heat up the water, rather to feed water. But you also need to keep in mind that if we allow that steam to work turbine, then perhaps the amount of heat that must be rejected in the condenser will increase. So, from that point of view, it is quite possible to increase the overall efficiency, though we are sacrificing somewhat amount of work by extracting steam from the turbine. So, next our objective should be to draw the TS diagram. If we can draw the TS diagram, that will help us to understand more about this cycle. So, this is the TS diagram, let us draw. You know that we are trying to draw all the processes in TS plane. From there we will come to know about all the processes by which eventually the efficiency of the cycle is getting increased. Okay. So, this is the boiler pressure, right. So, this is boiler pressure, and this is the condenser pressure. Okay. Now, so this is the amount of steam which is extracted from the turbine at an intermediate pressure. So, if we now draw the intermediate pressure, so this is the intermediate pressure. Intermediate pressure. So, if we try to draw the, say this is 0.5, this is 0.6 and this is 0.7, right. You can understand, if the fraction of steam that is extracted from the turbine is M1, then if 1 kg of steam is allowed to go to the turbine from the boiler, and if we extract M1 kg of steam from the turbine, remaining 1 minus M1 kg of steam will be allowed to expand isentropically and to go into the condenser. So, you know that this is basically m1 kg and this remaining 1 minus m1 kg is, so we have extracted m1 kg of steam from the turbine and remaining steam is again expanding isentropically up to the condenser pressure, that is 6 to 7, and this m1 kg of steam is extracted, but before that this amount of steam has done work on the rotating part of the turbine, and by this steam has done work while expanding isentropically in the turbine, that is 5 to 6. Okay. Now, you see that 1 to 2, again try to apply your common sense, because pump cannot handle two phase mixture, mostly it is liquid. So, the thermodynamic state at point 1 is saturated liquid. So, this is point 1, right. What about the pressure 2, 3 prime, 4 prime and 5? So, you understand this is not the open type, this is closed type. So, this pump is responsible to build up pressure, and that is the pressure at which boiler is operating. So, P2 equal to P3 prime equal to P4 prime equal to P5. That means 2, 3 prime and 4 prime, all these state points will lie on the boiler pressure line. So, this is 2, okay, and let me complete this 1. Okay. What will be the position of 3, 3 prime, 4 and 4 prime? That is very important. That is very important, right. See 2 and 3 prime, you know that so 3 prime is 3 prime, 4 prime and 5, these points are on the same pressure line. So, this is say 3 prime and what would be the 4 prime and 4? Question is, will the entropy at 4 be higher than the entropy at 4 prime or vice versa? That is very important. So, this is 3. Now, what is point 3? So, the 3 is again this saturated liquid. So, pump is used to supply that condensate, though this is two phase mixture, but that 3 is on the saturated liquid line. So, this is the 3. So, this point is 3 prime and this point I am marking, that is 3. So, I am using red color and this is 3. So, this red point is 3, this red point is 3 and 3 prime is on the other pressure line. So, this pressure 3 prime is definitely higher than pressure 3 and that is why the requirement of additional pump into is coming into the picture. So, 3 and 3 prime is at the the pressure at 3 prime is on the feed water line. So, pressure is the boiler pressure, while the point 3 is on the saturated liquid line. So, the pressure is high. Now, what will be 4 prime or 4? Ideally, point 3 prime, 4 prime and 4, all these points should coincide, but if you apply your common sense, that m1 kg of steam is extracted from the turbine, it is now allowed to pass over the coil. During the process, the extracted steam releases heat and that heat is absorbed by the feed water, while the steam is collected at point 3, that is essentially condensed steam. So, temperature, you know, you have studied in heat transfer courses, in heat transfer course, that it is very unlikely that the temperature of water. So, this is water is one stream which is whose temperature should be increased by taking heat from another stream that is allowed to pass over the coil. So, it is very unlikely that the temperature at 3 prime should be equal to temperature at 3, but it can, right. So, temperature at 3 is definitely higher than 3 prime, though I could not represent at per scale, but you should keep in mind temperature at 3 should be slightly higher than temperature at 3 prime, otherwise heat transfer will not be justified, and that is what you have studied in heat transfer course. That is why now what I should do, I should erase this point and I will write this 3 prime is here. So, this is 3 prime. So, temperature at 3 prime should be slightly lesser than temperature at 3, otherwise efficient heat transfer will not be justified. So, next is what about 4? Now, entropy at 4 is rather should be slightly higher than the entropy at 3 prime and 4 prime, because temperature at 3 is high and that is again pumped. So, while we are pumping, it is because of this viscous heating, temperature will increase little more. So, entropy at state point 4 should be higher than the entropy at state point 3 prime and 4 prime, and that is why the point 4 prime point 4 would be here. I am using so this is 4, and if I use this is 4 prime. So, this is very important, I hope you have understood. So, temperature at 3 prime is less than temperature at 3, entropy at 4 should be higher than entropy at 3 prime and 4 prime, though the points 3 prime, 4 prime and 4 should coincide, but theoretically they should not, right. So, since the temperature at point 3 is high, that condensed steam is again pumped. So, because of viscous heating, temperature will increase little more, and as a result of which entropy at 4 should be even higher than the entropy at 4 prime, and that is what you can see from the TS plane. So, this is basically so this is 3 to 4. So, this is the case 3 to 4 that I have shown over here, right. So, this is isentropic process 3 to 4, because that is again reversible adiabatic process pumping. So, I should show here W in 2, and this is also W in 1, right. So, this is all about the description of the regenerative power cycle with closed type feed water heater. What you can see, again I am telling, had this arrangement not been there in the circuit, the temperature of feed water would have been T2 before entering into the boiler, but it is because of this complex arrangement we could increase the temperature of feed water before it enters into the boiler up to 4, you can understand 4 prime. So, it is because of this increase in temperature which is temperature of the feed water, average temperature of heat addition increases, which in turn increases the efficiency of the cycle. Now, again one important issue will be there, that what should be the fraction of steam that should be extracted. In the context of the open type feed water heater, I have discussed that you you have to keep in mind that the thermodynamic state at the inlet to pump 2 should be the saturated liquid. So, that was the key for the calculation of the fraction of steam that should be extracted. So, again if you would like to calculate the fraction of steam that must be extracted from the turbine essentially in the context of this closed type feed water heater, we can again apply steady state steady flow equation to the this closed type feed water heater, and then we can easily calculate. So, let me write over here, that is, so this is closed type feed water heater, right. Closed feed water heater. What we can do? We can easily calculate this fraction of steam by applying steady state steady flow equation to the processes which are there in the closed type feed water heater. By how? You can calculate, so by applying steady state steady flow equation to the closed type feed water heater. What we can write? M1 into H6, M1 into not H6, M1 into H6 minus H3 to be precise. So, we can write why I am writing H6 minus H3, because this is not getting mixed directly, right. So, still the condensed steam which is collected at state point 3 is having high temperature. So, high enthalpy. So, M6 M1 into H6 minus H3 is equal to 1 minus M1 will be equal to 1 minus M1 into H3 prime minus H2. H3 prime minus H2. Okay. So, what should be the expression of M1? So, let me write in the next slide. So, this basically the feed water which is 1 minus M1 kg, entropy of the feed water increases, enthalpy of the feed water increases from 2 to 3 prime, and that is the increase in enthalpy. So, ideally you know that this is basically heat balance. So, the gain in enthalpy by the feed water is equal to the enthalpy loss of the extracted steam. So, if we try to write M1 into H6 minus H3 equal to 1 minus M1 into H3 minus H2, M H6 minus H3 plus H3 prime minus H2 equal to H3 prime minus H2. So, this is the expression M1 equal to H3 prime minus H2 divided by H6 minus H3 plus H3 minus H2. So, this is the fraction of steam, this is the expression of the fraction of steam extracted from the turbine. So, this is the important part. I am not going to write the expression of Q in, W out, W in 2, W in 1 and Q out, because you can apply again by, you can calculate again all these expressions by applying steady state steady flow equation to boiler, turbine, to the process which is there in the boiler, turbine, condenser and these two pumps. So, this is P 1. Okay. So, this is P 1. Now, we have discussed about several issues related to these several cycles starting from the Carnot cycle, that is the ideal cycle. We have discussed about the limitations of the Carnot cycle, then simple ideal Rankine cycle with several modifications, and then we have discussed about the regenerative Rankine cycle. And we have seen that by making use of this regenerative principle, it is possible to increase the efficiency of the cycle, which is which would be almost the Carnot cycle efficiency. It is not so easy to achieve the efficiency which would be as good as the Carnot efficiency, but of course, it can be increased closer to that of the Carnot efficiency. So, we have so far discussed about the cycle, and we have seen that the working substance of the cycle is water and steam water mixture, to be precise. So, now we shall briefly discuss about the ideal working fluid. So, if we write the ideal working fluid, you know that water is predominantly used as the working fluid in the vapor power cycle, though it is not an ideal fluid. Why? Because water is having a few drawbacks to be used as the ideal fluid, but you know that the concept of another cycle, that is known as binary cycle, will be an attempt to overcome those shortcomings of water and make water as an ideal fluid. So, though water is not an ideal fluid, but it is predominantly used. Considering this, at least now time has come to understand the important characteristics of the working fluid for the consideration as the ideal fluid. So, I will be writing here that important of the working fluid to be for the consideration of as the ideal fluid. So, let me repeat again, we have seen as of now water is used as the working fluid for all the cycles we have discussed till now, but though it is used predominantly, but water cannot be considered as an ideal fluid because water has a few drawbacks. But as I told you, the concept of binary cycle would be an attempt to overcome those shortcomings, so that water can be considered as the ideal fluid for the vapor power cycle. Before going to that particular cycle that we will discuss in the next class or next to next class, let us briefly discuss about the important characteristics of the working fluid for the consideration as the ideal fluid. What are those? Number one is high critical temperature. So, what is critical temperature? You have studied in thermodynamics. Now, question is, if the critical temperature is above the metallurgically allowed temperature, maximum temperature to be precise, then isothermal heat transfer is possible at the maximum temperature, because you know that we have seen that you know from the cycles that when heat is supplied in the boiler for the conversion of water into the steam, the low temperature heat addition is not, you know, what I am telling, what I would like to say is not desirable one, because it lowers the average temperature at which heat is added. So, if I now come to the Carnot cycle, you have seen that if we can increase the temperature at which heat is added, that is again, you know, heat transfer, isothermal heat transfer when fluid changes the phase. So, question is, I mean, if we can increase the critical temperature. So, basically if the critical temperature of the fluid is higher than the metallurgically allowed maximum temperature, because we cannot increase the temperature inside any device, otherwise the device, the material which is used to fabricate the device will start melting. So, if the temperature, if the critical temperature is above the metallurgically allowed maximum temperature, then isothermal heat transfer is possible at the maximum temperature as the fluid changes its phase. So, this is very important. You have seen that if the critical temperature is very high, and if we can have heat transfer, isothermal heat transfer at the maximum temperature, then we can closely reach at the Carnot cycle, towards the Carnot cycle. But at the same time we have to keep in mind that maybe the working substance will be having high critical temperature, but the saturation pressure should not be very high, that is very important. So, here should not have high saturation pressure at the critical temperature. Right. So, this is number 1. Number 2 is low melting point temperature, right. So, low triple point temperature. So, low triple point temperature. If triple point temperature, low triple point temperature. If the triple point temperature is low than below the cooling medium, then solidification can be avoided, right. So, if the triple point temperature becomes below the cooling medium temperature, rather below the temperature of the cooling medium, the problem associated with solidification can be prevented. Let me tell you again once again, let me tell you once again, you know that we need to reject heat in the condenser in which cooling water is circulated, and as I have discussed, all the condensers are operated at a pressure which is less than atmospheric pressure. If we can reduce the condenser pressure, perhaps we can allow steam to expand even more in the turbine. But the problem is, if the condenser pressure is well below the atmospheric pressure, air leakage will be there, and in addition to that, you know that that pressure at which condenser will be operated depends on the temperature of water which is available in the site. So, if we can have one working fluid whose triple point temperature is even, you know, less than the temperature of the cooling medium, then solidification problem can be avoided. Otherwise, what will happen, you know, it will start solidifying. So, that is number 2. Number 3 is, which is very important, that is low condenser pressure. Right. So, this is the low condenser pressure is not permissible. So, low condenser pressure is not permissible, that is what I have discussed just now, that it will create another problem of having air leakage into the condenser. If that is there, then we need to have again de-aeration, that is nothing but the removal of air from the feed water, otherwise it will start corrosion in the boiler tube. And number 4, which is very important, that is high enthalpy of vaporization. High enthalpy of vaporization, that is HFG, then isothermal heat transfer to the working fluid is possible. So, I am writing over here, this is very important, that isothermal heat transfer to the working fluid is possible, right. And finally, I would like to write another important point, that is 5. The working fluid should have good heat transfer characteristics, non-toxic, non-corrosive, inexpensive, readily available. So, 5 I am writing good heat transfer characteristic, and 6 is non-corrosive, inexpensive, right, readily available, and then is non-toxic. I am not going to discuss about points 5 and 6. You know that good heat transfer characteristics, that is heat transfer coefficient should be high, so that it can carry maximum amount of heat, because essentially what we have understood from the discussion we have till now, heat is added in one part of the cycle and in other part heat is rejected, and by this course of heat addition and heat rejection we are getting work output. So, the high temperature part of the cycle wherein heat is added to the working fluid. So, we should have the working fluid should have high heat transfer characteristic or good heat transfer characteristics. The last point, that is quite common, you have studied in the context of heat exchanger, which fluid is used. It should not be corrosive, it will be available readily, inexpensive and non-toxic, because this working fluid is allowed to pass through the coils tubes in the boiler. So, if these properties are not there with the working fluid which should be chosen, and then operation I think it will again invite cost associated with the regular maintenance of the different parts of the steam power plant. So, that if we would like to summarize today's discussion, starting from this open type feed water heater, which we have discussed in the last class, just to make a comparison between these two. So, open type feed water heater is relatively simple in design, it does not involve complex design. Since it does not involve with the complex design of the circuit, feed water circuit, I mean closed type feed water, open type feed water heating circuit, the maintenance cost is also less. Only one problem is that in this circuit the requirement of pump 2 is must, but if we go to the closed type feed water circuit, it is complex, maintenance as well as the initial cost for this circuit is relatively high, rather higher than the open type feed water circuit, but this circuit, I mean we can remove this particular pump. This pump is not essential for this circuit, instead we need to use steam trap. So, these are the basic comparison between the open type feed water and closed type feed water circuits in the context of the regenerative steam power cycle. And finally, we have discussed about the important characteristics of the ideal working fluid, which is commonly used in the steam power cycle. So, with this I stop here today, and we shall continue our discussion in next class, and we will discuss about the binary cycle. Thank you.